Okay, so next up in our series of videos on limits, we're going to look at one-sided limits. So one-sided limits are what you need when you don't want to deal with functions, for example, this piecewise function, where you don't necessarily have the same y values on either side of some particular point. So we can see for the graph that's drawn here, if I was interested in what's going on, let's say near x equals 1, well, if I'm just a little bit to the right of x equals 1, I've got y values that are close to 2. If I'm just to the left of x equals 1, I've got y values that are close to 4. Right? So I don't have this agreement on either side of 1. If I remember that when we talk about a limit, right, we have to allow for the possibility that x could be approaching a from either side. We might be looking at values where x is less than a. We might be looking at values where x is bigger than a. And in order to be able to say that the limit exists, we have to make sure that we can make those values of f of x as close to L as we want. And well, there's no way that I can find y values that are simultaneously close to both 2 and 4, right? There's no way. Those are always going to be a distance of 2 apart, so I cannot make this gap arbitrarily small. I'm stuck with this gap. But I can, of course, looking at this graph, it does seem to make sense that if I was only considering values of x slightly less than 1, then yes, the y values are getting close to 4. If I was only considering x values slightly bigger than 1, then yes, the y values are getting close to 2. So this is the idea for left and right hand limits. Here are the definitions. Right? So we talk about a limit, we consider x approaching our value, in this case c. Oh, I wrote a. Let's fix that. I guess it's easier to make a c into an a than it is to make an a into a c. So let's do that. There we go. All right. So we talk about a left-hand limit, or we say that x is approaching a from the left. This means that we can make the value of f of x as close to L as we want by choosing values of x sufficiently close to a, not c. Okay, but when we choose those values, we are only considering values of x that are strictly less than a. And the way we denote this, note the notation here. Okay, you see that superscript, the minus sign. This is superscript on the a. This is the notation that we use to indicate that we are only considering values of x less than a. This is the notation for the left-handed limit. So this expression here, you would read that as the limit of f of x as x approaches a from the left. Similarly, if x is approaching a from the right, well, that means that you're only considering values of x slightly bigger than a, right? So you're getting closer and closer to a, but you're staying on the right-hand side of a. You're considering x values that are bigger than a, and the notation for that is this superscript with the plus sign. So this is the notation we use for left and right-handed limits. So we're still considering values of x that are getting really, really close to this number a, but we're sticking to one side or the other because of situations like we saw in the previous slide. Okay. Now, there is a close connection between these one-sided limits and the original limit, right? If we want to have a limit at a point, well, then we need to be approaching some common value, regardless of whether we're coming in from the left or from the right. And so that one of the tests that we use to establish whether or not a limit exists, and this is something that we might commonly use if we were dealing with, say, piecewise functions, where the function is given by a different formula depending on what interval you're in, right? You might want to figure out whether the limit exists at a certain point. Well, one of the ways to figure that out is you calculate the left-hand limit, then you calculate the right-hand limit, and if those two limits come out to the same value, then you would say, okay, the limit exists, right? So this is the idea, is that the limit can't depend on the direction in which you let x approach a. So in order for the limit to exist, these two directional limits, coming from the left and coming from the right, they need to agree. Let's look at another graph so we get an idea of how this works. Okay, here's, I think I threw this graph up in an earlier video, and we can see there are 3 points here where limits are going to fail to exist for these two functions, right? If I consider the function f of x and I look at, say, 0, I can see that the limit as x approaches 0 from the left of f of x. So that means I'm considering values that are to the left of the y-axis here, slightly less than 0. Well, I can see that the y values are coming, it looks like they're getting really close to 1, so the y values are coming in towards 1. Right? If I was considering the right-hand limit, x is going towards 0 from the right of f of x. Well, as I come in from the right, we can see that as I come in from the right, my y values are getting closer and closer and closer to 0. Right? And because those two limits are not equal, if somebody asked, well, what's the limit as x approaches 0, we would have to say that the limit does not exist. Right? And we could play the same game at x equals 2 for f of x, or if I was dealing with the function g of x at 1, well, I can't quite tell what that value is there, right? But it looks like the limit as x approaches 1 from the left of g of x is, I don't know, where does that look like to you guys? It's about 1 and 2/3, let's say. So what's that, 5/3? I don't know. I'll put approximate signs. I don't know quite what that is. On the other hand, if I was coming in from the right, well, as I come in towards 1 from the right on the graph of g of x, I can see that the y values are getting close to 3. Okay, so that's how you analyze this sort of thing graphically. If you want to analyze things analytically, well, often it helps to kind of look at both the formula and the graph. Let me quickly sketch out what does this thing look like here if we were to sketch it. Well, we've got a line y equals 1 minus x when we are less than minus 1. So that's going to be something like this. Okay. And when x is actually equal to minus 1, so that's at 2, 3. So the y value is defined to be 3 when x equals minus 1, and then between minus 1 and 1, we've got this parabola, and then when x is strictly bigger than 1, we have a square root. So let me I'll put that square root in a different color. Okay, so there's the graph. And looking at this graph, well, you can see from the graph where the limit is going to exist and where it's not going to exist. So certainly for, in any of these intervals, less than 1, between minus 1 and 1, bigger than 1, we don't have to worry, right, because we can calculate all those limits by direct substitution. The only places where we've got to be careful are at these points where the formula changes. Right? So if I was looking at minus 1, right, as x is approaching minus 1, we say, okay, what happens as x approaches minus 1 from the left? Well, if x is coming in from the left, we say, okay, that means x is less than minus 1. So if x is less than minus 1, what formula am I supposed to use? I'm supposed to use, when x is less than minus 1, I'm supposed to use 1 minus x. Okay, and I can do that by direct substitution. I plug in x equals minus 1, and I get a limit of 2. Right? So as far as evaluating the limit, notice that left-right-hand limit, this doesn't matter. You still just plug in the values. But where it matters is, whether we're doing the left or the right-hand limit, it tells us which formula we need to use. Because if I was going to come in towards minus 1 from the right, well, if I'm coming in towards the right, then I need x to be bigger than minus 1, so I'm here, and I need to use x squared. Right? Remember that we're considering values that are bigger than minus 1, but still close to minus 1. So I don't care what happens out at this end when x is bigger than 1, right? I'm just a little bit bigger than minus 1, so I'm in this region here. So I use x squared, I square minus 1, and I get 1. And of course, those two limits are not the same, right? These are not equal. And so I can tell you that the limit does not exist as x approaches minus 1, right? So we could put that up here. We could say the limit as x approaches minus 1, f of x does not exist. On the other hand, we could do the same analysis at 1, Right? And if we let x approach 1 from the left, we'd be using x squared. And let's just look at the graph for this because we're out of space. If we come in from the left using the x squared function, well, the y values are getting close to 1. If we come in from the right, we're using the square root function. But again, the y values are getting close to 1. Those agree, so the left and the right hand limits, they're both equal to 1, and so the limit also would be equal to 1. So we do have a limiting value there at x equals plus 1. We don't at x equals minus 1. One other remark before we close this video, notice that the actual function value at minus 1, I define that to be 3. Doesn't agree with either limits, we don't care. Remember that when we're evaluating limits, we're considering values that are close to the point, but we're not actually looking at the point. So this value here is completely irrelevant to whether or not those limits exist and whether or not the limits agree. When we look at the limits, we're looking at this function and we're looking at this function. Okay, that's it for one-sided limits. We've got a couple of videos on infinite limits coming up.